Hi guys, Mr. Bouchard here, and today I'm here to talk to you about fields and isolines. Okay, so fields are any measurable quantity in science. So if we map out an area with some sort of levels of temperature as an example, all right, so we could put thermometers around this room, get the temperature at each point, we can make a field map. Okay, so fields are the actual measurable quantities. Usually we don't have enough data to get every single point in an area, all right, because it would take a lot of devices. So what we do is we kind of map them out, all right, and we can map out any of these measurable quantities, including gravity, magnetism, temperature, sound levels, elevation, which we'll be doing next more in detail with contour topographic maps. Depth, pressure, wind speed. So any sort of weather-related things can be mapped out in this way, and we'll definitely be using that later on this year. Okay, so I'm going to do my first example, and I'm going to use sound as my example in this case. So if we're dealing with a speaker, that could be our sound source. And if we have the students sitting out in the classroom here, all right, they're going to hear the sound differently depending on where you're sitting. All right, because the sound waves, they travel out from the speaker in every direction. Okay, but what happens naturally, the ones that are closer will hear the sound louder. That makes sense, because what the sound waves do equally, they wrap around this area, and where I'm drawing these lines, that's where the sound level is going to be equal to the students. Okay, so we could put numbers to this. Decibels is a common measurement of sound level, so I'm going to make that our unit. So 92 decibels, this could be 90 decibels, this could be 88 decibels, and then 86. Now 86 doesn't show up here, all right, because we ran out of room in the room, and that happens occasionally, all right, and it will show up, it will go still to the corners. All right, but back here you don't have an 86 data for 86 because it's going to be somewhere between 88 and 86 in this area. So we can use this to predict areas. Okay, so even though we don't have data, we could say we could pick a point here, make this point X, and we could predict that X is around 89 decibels. All right, so that's the use of ISO maps. We can figure out in between values by plotting on a map, and this is something you guys are going to have to do in questions occasionally, estimate the value at a certain point on the map. Also, what you will sometimes have to do is figure out the isoline interval. So in the case of this sound level interval, interval means what the lines are counting by, basically. So what's the next consecutive line? So in the case of this, the isoline interval is going up by 2 decibels, right? Because 92, 90, 88, 86. So we're counting by twos. All right, so that's something you will occasionally have to figure out. I'll give you other ways when we get to contour mapping, where you'll be able to figure out a rule to figure it out all the time. Some of these maps you'll just have to figure out calculating or counting to figure out the interval. Okay, so isolines are any point of equal field values. So an example here, so these were isolines for sound level. Okay, you could have temperature, you could have pressure, you could have any sort of measurable quantity in that same way. So in the case of isotherms, which we use in weather, let's move this out of the way, that's a line of equal temperature. Okay, so you guys have seen that on Weather Channel. When they show a weather map and they show the different colorings, they'll show reds, oranges, yellows, greens, and they associate with certain temperature ranges. If you see a 90-degree temperature range, it's going to be shaded red. 80-degree might be orange. 70-degree might be yellow, okay, and so on. So you have to have the isotherms connected up before you did that shading, which they did on the maps. Isobars, these are points of equal air pressure, all right? That's one way we map out storms, because we look at their pressure. We can see if storms are strengthening, if there's more isobars showing up. So that's something we do, mapping that. And then contour lines, of course, points of equal elevation, and we'll be dealing with those with contour maps, topographic maps, which we'll be looking at in the next part of the chapter. Okay, so that's isolines. Here's another example. Okay, not to take away from the last one we did. Same idea, but this is temperature this time. And I made it kind of straight just to make it easy, a simple example. So we have 29 degrees Celsius here, 28, 27, 26. So all along the lines, guys, are the same temperatures. In between will actually be values in between. So we can map out the temperature in the room, and also this can be used to figure out where heat is moving, heat is escaping to. And this is something we do to actually make sure our homes are efficient. Okay, so an example here. So this would be considered to be the warm part of the room. All right, so we sometimes label this as the source. So that's where the heat is coming from. All right, so there might be something warm over in that area. It could be actually physically a heater. It could also just be maybe a refrigerator or something that's giving off heat. There's something warmer over in that area of the room. Okay, and over here it's cooler, so this is a heat sink. And a sink can be where the heat is escaping to. All right, maybe there's a window over in this area. Maybe there's a vent. So something where the heat is escaping to. So the heat is really flowing from source to sink across this room, out that way, just like the sound waves were before. And that's why the heat is equal along the lines this way, perpendicular to it, the way it's flowing. And we can also predict, once again, values in between. We know there's a 1 degree interval between the isotherms. So we can predict the temperature at a certain point. Okay, so if I say that's point X there, we could say that's 27.5 degrees Celsius. Okay, you can predict what the temperature is at a point exactly by looking at the map and estimating what you think it is. So it's a great little tool, and we'll be using it again in weather and, of course, mapping, what we're going to do in the next part of the chapter. Okay, so source and sink again, and heat flows from source to sink, so I already showed you that. Okay, lastly, I want to show you an example here. This is a mapping of solid air pollutants. Okay, so once again, mapped out, and we have a factory here which is giving off pollution. And you notice that the pollution is flowing in this direction. So maybe there's a wind in that direction that's blowing in that way. So there's your source. So we could have again, a factory, and that's the data that's coming out of it. All right, so, and whatever the units are, so you read what in the example. So this is solid pollution in particles per centimeters cubed. So that's the units. So you can read that off on the map. Also important, which I didn't mention yet, if you have a map, we can also have what's called a map scale. And when you see a map scale, this tells you distance on the map. The way I use it, I use a piece of paper alongside of this. That's the easy way to use the map scale. So if they're going to make you measure between B and E on the map, or B and F, if you take a piece of paper, mark those 2 points, and then bring it down to my scale, it's an easy way to measure using distances. All right, so I will show you an example of gradient in a moment, because we have to do that again under the camera. But this is the basics on how to read the map, and we'll be looking at this example on how to calculate gradient in a moment. So I thank you guys for tuning in, and like I said, I'll continue with the gradient example under the camera.